It looks like the light is this big, when in fact it's only this little bulb that's generating all the light. It's just that we see it being reflected off of this shiny mirror kind of object. All of the conic sections can be described or defined in terms of distance. For the ellipse, we can understand the distance definition with a little experiment. Suppose we drive two nails into the board like this, and we drape a string between the nails. Then we take a pencil and we stretch the string and draw the figure. Now the figure will be an ellipse. Now the string stretching sort of gives us an idea of the notion of distance here. If we take a point on the elliptical curve and we add the distance to those two nail points, add this distance and this distance, then we get a total. Now that total is the same for any point on the ellipse. That is, the total of these two distances would be the same as the previous total. And that would be the same for any point on the ellipse. And it only makes sense because the total of those two distances would be simply the length of the string that we started with to draw the figure. Well, let's talk about some terminology. The two points that were designated as the nails are called focus points, and the plural of focus is foci. If we identify a point right in between the two focus points, we're identifying the center of the ellipse. Now, a segment that goes through the ellipse and actually connects from one end to the other, but containing the center and the two foci is a major axis. At the end of the major axis, there are 2 points called vertex points or vertices. The segment going through the center, perpendicular to the major axis, is the minor axis. So here's the length of the minor axis, here's the length of the major axis. Now, if the ellipse is elongated vertically, like this, then the major axis will be vertical and the minor axis horizontal. Let's review the terminology. We have a center point, we have these 2 points as focus points, and these 2 points vertex points. Now let's talk about building an equation that gives rise to this ellipse. First, let's assume that the ellipse is situated so that the center of the ellipse is at the origin of the coordinate system. Now, it may make some sense that any equation describing the shape of this ellipse will need to give us information about the distance from the center of the ellipse to the end of the major axis, and also information about the distance from the center of the ellipse to the end of the minor axis. Well, if we call these distances A and B, then the equation describing this ellipse is this equation. Notice a plus sign appears between the two fractions and a 1 appears on the right side of the equation. And another interesting thing to realize is that A and X are both horizontal distances on the graph, and A and X appear in the same fraction of the equation. In a similar way, B and Y are vertical distances, and B and Y appear in the same fraction. When the ellipse is elongated vertically, the equation looks like this. Notice that the B squared and A squared appear to simply be swapped in this other equation. And that kind of makes sense when we think about the distances involved. Now, we know that A is the distance from the center to the end of the major axis, and B is the distance from the center to the end of the minor axis. Well, A and Y are vertical distances of Tripsy. Point at 2, 0. That tells us information. Point at 2, 0. A focused stone. A most interesting characteristic of the ellipse is a reflective quality between the foci, as shown here. An emission from one focus will bounce off the wall of the ellipse and reflect upon the other focus. This characteristic is used in a process called lithotripsy, which is a hospital procedure that disintegrates gallstones and kidney stones. In the procedure, the patient is placed into a liquid medium and half of an ellipsoid is positioned so that the stone is at one focus. Using an electrical gap, a disturbance is created at the other focus. The disturbance emanates from the focus in all directions, bounces off the wall of the ellipsoid, and concentrates its impact on the stone at the other focus.
Using repeated disturbances, the stone is disintegrated. Here's a portion of a film clip about lithotripsy.
In completely unbloody extracorporeal lithotripsy, the essential thing is exact positioning of the kidney stone in the body at the focal point of the shock wave ellipsoid. This is facilitated by a stretcher, which is hydraulically adjustable in extremely small steps, and on which the patient is strapped so that the kidney area of the back lies exposed above the half-open ellipsoid. The shock wave is generated in the first focal point with the help of the shock wave electrode. Two X-ray image amplifiers permit precise three-dimensional positioning of the stretcher so that the kidney stone is placed exactly at the point of maximum effect of the shock wave. As soon as the stone appears in the crosshairs of the X-ray monitors, the doctor can begin applying the shock waves. Generated in the ellipsoid underwater, the shock wave triggered by the electrode passes through the water in the bath into the patient's body, reaches the kidney stone, and disintegrates it to a fine-grained debris. The destruction of the stone structure is caused by the high-pressure amplitude in the second focus of the ellipsoid. In the course of a treatment, about 800 to 1,000 shock waves are reckoned with, which as a rule are automatically controlled in rhythm with the heartbeat. On the X-ray monitor, the disintegration of the stone is already clearly evident.